Okay, today is the 20th of October, 11 more days till Halloween. I know Mr. Ravi Kumar is looking forward to that. Are you going to dress up for Halloween? Like American Indian?
That's very curious you say that. Someone else made the exact same joke. I made the exact same joke too. Oh yeah, it was him.
I guess you're sandwiched in. That's terrible. I'm shut up. One of my students today filmed himself on a skateboard dressed as a ghost for Halloween. And this is what happens when you have children, okay? So now we'll talk about WellboreStrg. Let's go around the room. Alex, what's the worst day of the year? I love it. Nailed it. Hit it right on the head. We don't have to go another step. So tell me, what do you hate about taxes? But don't you believe you have to pay for freedom? Yeah. They're all laughing. You want me to quote George Bush? Freedom ain't free, right? So, WellboreStrg is a tax. You're going to pay it one way or the other. We have two systems. We have a gigantic reservoir, and we have this little tiny straw that goes into the reservoir. Unfortunately, that little tiny straw is actually a separate system. And what does it have in it? It has its own fluid system, and that fluid can rise, or it can have gas in it, or it can be compressible. Okay? And it acts like what? If this were a mechanical system, it would act like a spring. But this isn't a spring. This is a dampening coefficient. If you can think of WellboreStrg like that, you're going to be okay. You have to do the following. You either have to wait for the dampening coefficient to die off, or you have to change the system. Who worked for Schlumberger? Halliburton? Baker Hughes? Nobody? Mr. Liu smiling. You would gladly take a job? Okay. No. Nice answer. So these people sell services. They sell equipment or they rent equipment. What they would love to sell you is a device that goes down in the wellbore and somehow shuts off the volume at the bottom of the wellbore. So really quickly, and math ladies, I know barrels don't make any sense to you. They're 42 gallons, okay? You know what a gallon is? Like milk jugs? That's a gallon. So there's 42 of those in a barrel, okay? You got that? So the distance is, it's about 2 inches, maybe two, well, that's bigger than that, maybe 2.5 inches at the most tubing, maybe some of it's about 3.5, whatever it is. So the distance is several kilometers down to the bottom, and you've got a cylinder of volume. It could even be this big. How many barrels is that? How many gallons of milk is that? Or how many gallon jugs is that? Is it a lot? Like dozens? Cam? You're in drilling. You have to know how much is in the wellbore at all times. I really hope that you get a nice internship on a drilling rig. They're going to torture you. Let me give you a piece of advice. If they throw you in the mud pit, don't try to swim. Just try to float. Things don't come back up once they go down. So they'll dig you out whenever they sell it to the farmer. Yeah, I know you will. Okay, roughly speaking, how many barrels? Maybe 30, 40, 50, maybe even 100 barrels of fluid. This doesn't seem like very much, but when it's under pressure and it's compressed, that's a pretty big dampening coefficient. In fact, what happens when you open the valve in your water hose? You guys know? The hose inflates and it's under pressure, and then when you turn it off, you can still spray it because it's under. It's actually not the water that's compressed, it's the hose that's stretched, but the analogy still sticks. Okay? So what happens if I have a pipeline that's 3 or 4 miles long and is under pressure, and I open a valve on this side? Do I feel anything over here? No. But it's producing fluid out of that side. What is it producing by? Expansion of the fluid. Okay? And exactly the same principles are going to apply here. So what I'm trying to say is when I'm at the surface, when I'm here, and I've got a well that goes down 3 or 4 kilometers, maybe 5 or 6, and I open the valve at the surface, what's happening downhole? Nothing. Let me repeat, nothing. Okay? Cam, drilling question, you ready? Completely unrelated. You're never going to talk to me again, are you? When you start turning the rotary table at the top, how many times do you have to turn before the bit starts moving at the bottom? Just guess. Is steel elastic? Yes. So it could be a lot of things. It could be the depth. It could be the type of material. It could be everything else. But when you first start turning at the Kelly bushing, what's happening downhole? Nothing. Okay. They take 2 or 3 turns before it actually starts moving at the bottom. I'm just trying to give you an example of this is the kind of system you're dealing with. So you have this huge tax that you're going to have to pay. The only way to reduce that tax is to reduce the volume. Alex, you got an idea for how to do that? You're going to drop a tool down, and it's going to latch in place, inflate or something, and it will seal off the top from the bottom. Okay? How much does that cost? What kind of car do you drive? What year? So what's it worth? You know, this lecture is going to take forever. Give me a hint. Math ladies, you guys got a car? No. Yes? What kind of car? What year? 2013. Ah, that's pretty new. Okay. Is your car worth more than his? Probably so, because his was made in America. Actually, the Honda was too, but don't tell anybody. So, what do you think it's worth? $20,000? Yep. Okay. So, if it costs $6,000 a day to have that shut-in device, every 3 days, that's your pickup. Okay. Does Schlumberger care about how much it costs? Do you think that the service companies care about how much? Well, I mean, they care whether you use it or not. But, for example, if you have a choice between, say, $1,000 a day to put a pressure gauge in a well and $10,000 a day for bottom hole shut-in, what are you going to do? And what are you going to have to do? You're going to have to wait for the wellbore storage to subside. Now, as I mentioned, the reservoir, quote unquote, whenever that's happening, is the wellbore. And the wellbore is connected to the big reservoir. So you have to wait until the little reservoir does whatever it's going to do before you feel the signal from the big one. Very simple question. Math ladies, you ready? I'll point it at you. Ready? So when we have wellbore storage, what information are we getting from the reservoir? This is like Jeopardy. You want to throw a lifeline to the driller or to Buzzcut or to Gabe? Gabe, you want to answer? Whenever we're producing only from the wellbore, what information are we getting from the reservoir? None. Nothing. Zero. Nada. The only thing we're getting information from is the wellbore. And then as we begin to produce, and as the signal from the reservoir begins, we still have this dampening coefficient. And whenever that dampening coefficient still dominates, or influences but does not dominate, what information are we getting from the reservoir? It doesn't matter because now they're commingled signals. Can we extract them? Sure, if we have the downhole rate. Does anybody measure rate downhole? And if they do, how accurate is it? We're back to this dilemma again. So you have to wait until all of the signal is coming from the reservoir. So from a practical standpoint, very early times, the only signal you're getting is from the wellbore. Middle times, so to speak, you're getting reservoir and wellbore information. And then later, you're getting only the reservoir information. Okay? Everybody take a deep breath. Wellbore storage is simply a variable rate condition imposed on the reservoir. Now, you just had a lecture in convolution. You're graduate students. I need you to use inductive logic. If I have a rate profile that represents the system and I apply convolution, can I represent the reservoir? Yes. But what? That rate profile must be very, very, very accurate. In the mid-1980s, a paper was published by Schlumberger, by Meunier, Stewart, and Whitman. And what were they trying to do? Exactly what I just said. They were trying to use downhole rates to eliminate wellbore storage. It didn't work. You can model this, but you cannot apply it. As someone who's written several theses in deconvolution and a dissertation in deconvolution, yes, it is theoretically possible, but go add 5% white noise to the rate, and what do you get? A mess. So tonight we're going to talk about how to derive the wellbore storage relations. We'll do so quickly, and then you're on your own. So we have two possible conditions. We have a fluid-filled wellbore. Could be gas, could be liquid. It's under compression, just like I said. We open the valve at the top. You like this artist drawing? The artist is me, of course, so say yes. We open the valve at the top. What happens at the bottom? Nothing. But in time, eventually, flow begins at the bottom. Okay? Now, in this case, it's a pumping well. So there is a liquid level here. And so when we pump the well, the liquid level drops. When we stop pumping, the liquid level rises. How many of you know about our well out here by the other building? You've seen it over by geology. This is exactly the configuration of that well. Exactly. Only that well is a water well, okay? It goes down to about 400 feet. If you want to see some data from it, I can show you. It's in my P620 324 lectures. We used to run pressure transient tests on it all the time. And you would chase this water level with a resistivity device and follow it down. And then when you shut the well in, you'd follow it back up. This is your wellbore storage feature. Now, what we're going to have to do is define a mass balance on the wellbore. So m dot in minus n dot out is the differential, the accumulation term. So we set all this up, and I apologize for all the American units, but this is America. So then we do that, and we end up with an expression that's defined something similar to this. And so this says that the rate difference multiplied by the formation volume factor, because we have to work in reservoir barrels, is equal to 24. Why? Because we work in hours. And then we have what? The volume of the wellbore change over time. And we'll have to come up with whatever we think that is. What do you think is going to happen there? The volume of the wellbore change is going to be related to the compressibility of the wellbore fluid. Okay. So as we come over here, the limit of the change in wellbore volume over time is going to be equal to a derivative. Oh, sorry, I forgot to start out here. This is the material balance equation, exactly the same liquid material balance equation we've been using. The change in volume of the wellbore is equal to the pressure change multiplied by the compressibility multiplied by the original volume of the wellbore. So then when we set that up as a differential, take the limit, we end up with this expression. We assume a pseudo-steady state type behavior, which says that the change in average pressure in the system is equal to the change in the wellbore pressure. Is that accurate? Is that correct? Is it okay? That's probably fine. Okay. So when we do that, we equate these two relationships, and we have the change in wellbore volume is equal to the compressibility of the wellbore fluid multiplied by the total wellbore volume, the pressure at the bottom of the well, and then the pressure at the top of the well. Okay, so we had to have an influx term, which is this pressure at the bottom of the well. And what do you think we're going to do to make this easier? Well, we'll talk about that in a minute. So then we go on ahead and define our rates, and because the change in volume is actually rate. And then when we're finally done, we're going ahead and define our constant. Our wellbore storage constant is called C sub S, and it's just the wellbore volume multiplied by the compressible fluid volume. Or compressible, sorry, the compressibility of the fluid, my apologies. So we have the sand face rate, which is at the bottom of the well. We have the surface rate, which is Q. We have formation volume factor, 24, which is number of hours in a day. This thing, which is reservoir barrels per PSI. And then we have PSI per time, PSI per time. And this is the bottom hole pressure. This is the surface pressure. We'll talk about this more in a minute. Now, I will say that if you're staring at this, you're going, that is a really complicated equation. It's not, actually. It's a very simple material balance. And it tells you that the sand face rate, when you first start producing, is actually 0. The surface rate can be whatever it is. Now we're going to look at a rising or falling liquid level case. So the change in the wellbore volume, we have to, again, use the barrels conversion. Again, use the area in feet squared. But now we're looking at the delta, the change in height, which is here. So we have to know that. And when we do that, we set this up. We take it again as a limit is the change in volume with respect to time. The delta T goes to 0, so that becomes a derivative. And that tells us that the change in height with respect to the change in time, take the limit of that. We end up with the change in wellbore volume is equal to this conversion factor multiplied by the wellbore area multiplied by the change in Z with respect to time. And that, of course, makes perfect sense. So now we have to use the definition of what, Cam? What is this equation? What are you doing drilling? What's the only equation you know? Rho GH. Okay. So we have an equation that says what? That the pressure at the bottom of the well, PWF, is equal to the pressure at the surface, then multiplied by the density of the fluid. We got some stupid conversion factors, and we have delta Z. We also have to change inches squared to feet squared. So delta Z is equal to this, and then we take the limit as delta Z over delta T goes to 0. Of course, we end up with a pressure difference. We work this out. We make our final substitutions. Keep going. And lo and behold, what happens, class? When we're finally done, equation 17 and equation 9, completely different physical conditions, yield exactly the same equation. Their material balances on their system. Okay? So now we want to define this as a dimensionless rate, QD. So it's a sand face rate divided by the surface rate. And then we apply the definition of dimensionless variables. You'll understand this in a second. Once we've applied the definition of dimensionless variables, we have the definition of the dimensionless wellbore storage coefficient, and we have the definition of dimensionless rate. So the dimensionless rate that the reservoir is seeing is 1 minus some dimensionless wellbore storage coefficient, the derivative of the dimensionless wellbore pressure as a function of time, minus the derivative of the surface pressure in dimensionless form as a function of time. What is this rate at time equals 0? At the bottom of the well, what is this rate? 0. Okay. I also mentioned some other things about how Fair looked at this and how other people did things. If you integrate the previous version of this equation, which is given by QD is equal to 1 plus this stuff. If you integrate this, you get this final form. Now, why did I do this? Why did I eliminate the tubing pressure term? Why did I do that? I did this because we don't know what it is. The truth is, we want to simplify this expression. And this is a weak link. If you want to study more about where this is not equal to 0, then you have to go to the phase redistribution paper. Okay. Now, people knew what phase redistribution was before they knew how to model it. The equation 26 is fine. That is the correct equation to use. But we're going to assume what? That the surface pressure is constant. What's the derivative of a constant? 0. Is the surface pressure constant? No. But it will significantly reduce the complexity of this problem if we assume it is. Okay. So we make the same changes, and again, this is now the definition that we traditionally use in well testing. So it says that the dimensionless rate is equal to 1 minus the wellbore storage coefficient multiplied by the dimensionless pressure derivative. And what's going to happen is this term is actually going to be 1 at very early times, so the dimensionless rate is 0. Now, if we set this system equal to 0, what's going to happen is we were going to derive this expression. And this expression says what? That the initial pressure is the intercept of a series of data points where what's happening? Where the rate at the bottom of the well is essentially 0. So we're saying that it's 0. If it's approximately 0, we'll get this expression. And of what value is this, class? What's the value of that expression? This tells you that when you open the well, what kind of pressure profile are you going to have? It'll be exactly linear, but it has nothing to do with the reservoir. It has to do with the wellbore. Okay? If I take the slope of that line, can I calculate the properties of the wellbore, of the reservoir? Duh. Okay. I get the properties of the wellbore. So the exact same thing is true for the reflection, and the reflection is for a buildup. For a buildup, we're looking at the buildup pressure, but instead, what is the rate when you shut in the well at the surface, Mr. Liu? It's still flowing at the bottom. So we call that afterflow. So the opposite happens here. Okay? You shut the well at the top, so there's no flow rate. But what's happening at the bottom? Still there's flow rate coming into the well. So the degradation of that, or whatever you want to call it, the buildup signal is going to reflect the wellbore. Okay? So we continue to make this non-dimensional, and finally we end up with all these nice equations describing wellbore storage. Now, how do we solve, or how do we construct the wellbore storage solution? We already derived the expression for convolution. Okay? We need an expression for dimensionless rate. So what we're going to do is we're going to take the Laplace transform of the convolution form, and that'll give us this, no problem. But now we need what? We need the Laplace transform of the rate function. And the rate function is equation 26, but in this case we've assumed that the surface pressure is constant, and that goes away. So the condition is the initial pressure is 0. We have the Laplace transform parameter multiplied by the wellbore pressure dimensionless form, and this expression looks like this. Okay? So then when we substitute equation 34 into equation 33, we have this expression. We have PWD here, and we have PWD here. We need PWD on the left-hand side. So we divide through by PSD and PWD, and we get this expression. Okay? This is actually the deconvolution expression, because this is what we want to solve for. But of course, the reciprocal of the inverse Laplace transform is not the same as the Laplace transform of the reciprocal function. So this isn't going to work out very well, but that's okay. So we move this over and we solve for this expression. Now, how do you invert this, class? How can you invert that expression? This is the universal equation for wellbore storage. Every reservoir model that we've derived in this course can be substituted here. Every reservoir model that we've derived so far is the PSD function. We've derived the fractured well case, the naturally fractured reservoir case, the radial flow case, the linear flow case, etc. They all go right here. How do we invert that? This is really, really bad, right? Why? Because it's 1 over that. And I know you're saying, but it's 1 over that. Yeah, but there's a little trick here, right here. So let's try the case we know, which is the infinite acting line source solution, which is this. And when we substitute that in, we have this. Can that be inverted? Yes, it can, This is actually from Van Everdingen and Hurst, but Agarwal, Al-Husseini, and Ramey show how to do this. But this is not fun. Anybody else got any ideas on how to invert it? Is there anything else? We could try to use the log approximation, but we just end up with something still pretty ugly. We can cheat and use a sampling function known as the Chapery approach, but that isn't going to do us very much good. So again, very simple form of an equation right here. In the Laplace domain, this is a very simple relationship. All we have to do for any case where we want to know Wellbore storage is substitute our solution into that PSD term. But we cannot solve it explicitly. So what do? Alex? It's 9 o'clock. We stop class. We say, we'll just have to invert this numerically and walk away. Pan system, Kappa, Fouquet, Pi, Joe Schmo from Kokomo, my Piranha program, every one of them does this. Every one of them. You have to use numerical inversion to solve equation 35. Every one of them. You want to derive a solution to something, you want to create an addition to the petroleum literature that really changes something, figure out how to solve that equation. But remember what I just told you. The form is all wrong. Now, math ladies, this is where engineering gets a little weird. How would you solve it? Okay. Next guess. How could you solve it approximately? What if we came up for an expansion? Sorry? Say it again. Okay, so you would say that you would take this expression and come up with some sort of a mathematical expansion where you could then invert it. Is that, I'm putting words in your mouth. You like that? Yeah, okay. So how would you go about doing that? What strategy would you use? What's the only thing that will really give us the algebraic form that'll work here? Everybody knows. What kind of expansion? Asymptotic. Sorry? Asymptotic. Well, what I'm trying to think of is what looks really good in 1 over, what is a function 1 over f of u when that f of u is something, what is it that can be expanded? Or what is it can be solved directly? But not a plus, you're getting there. Sorry? Not exactly, but you're on the right track, both of you. It would be polynomials, okay? And the Laplace, if we assume that PSD was a polynomial, and we take that into that form, then algebraically we can rearrange it and solve it. But PSD is not polynomial. Everybody understand? PSD is not polynomial. It's logarithmic, it's full of Bessel functions, it's all these other things. But what could happen? So this is what the solution actually looks like. All right? This is the exact solution. This is a solution considering PSD to be a constant. So instead of assuming it's polynomial, we assume it's a constant. Okay? The black lines are the right answer. The dashed lines are the approximation. It works at the low end, and it works at the low end, works at the high end. So that shows some promise, but it doesn't work in the middle. So Mr. Liu, not good, right? Not good. Because we already know how to analyze the low end and the high end. Next is the so-called linear case. Simple equation like you were saying. Look how it works. It's almost indistinguishable. Okay. The black line and the dashed line. And then there's a quadratic form that's yet even better. Okay. But then reality sets in and we want the derivative. This is what the exact solution should look like. This is what the constant PSD case looks like. And remarkably, it matches extremely well throughout the range except for low values of WellboreStrg coefficient. And then we try the linear case, and it's a little bit better. It matches really well everywhere except here. And then we try the quadratic case, and it pretty much works everywhere. Okay. But math ladies, let me ask you a question. I cheated to do this. I cheated. The math gods do not forgive cheating, right? It turns out that we actually have a nice closed form for only one piece, which is the constant case. The linear case is a lot of algebra, and the quadratic case is a lot of algebra times a non-trivial integer. Okay, it's not really that bad, but you could solve this problem directly. What's the most important two-word question in the English language? What is it? So what? How does this help us? No habla? If we can solve this completely and explicitly, then we have promise of being able to use this as an analysis tool. But it's not good enough. Even though it looks good enough, it's not good enough. What does that mean? Can't? It means it might work, but in the sections where the derivative doesn't agree, it's not going to be good enough. And therefore, what's going to happen? We're going to get the wrong shape, the wrong interpretation, the wrong kind of behavior. What's the only thing that will work? Numerical inversion. Okay. I was really, this is one of those things I developed when I was just a little bit older than you. I told you I spent years working on convolution and deconvolution. So I thought, this will be the thing I'm famous for. I figured out the WellboreStrg formula. It didn't turn out that way. And I've had a couple of students work on this trying to improve it, but it ain't going to happen. You want to work on this, Eric? Why not? Is it impossible, or is it just not? It's probably not. Whatever we do to fix the issue is actually probably going to make it worse. Does everybody understand that? Because when Mr. Liu said this, when you're looking at asymptotic expansion, when you start playing around, the Russians love asymptotic expansions. They love early time expansions, late time expansions. And we always tried to solve the whole thing, but they had a good idea because they were looking at, but when you start trying to splice things together, what's going to happen? Do you guys know what a splice is when you take a rope and splice it together? What's the derivative of a splice? Something's going to happen. All right? Okay, let's quit before the other video stops.